Welcome to another edition in this series of videos, reinterpreting maybe conventional physics as it's presented in college lectures. So we were left off with a circumstance of surfaces and how you can measure their charge, and it's all in the context of this being an electric field that is creating a phenomenon, that it's causing effects in the world. And I contend there is no electric field. There's one field created by the circumstance of charge or magnetism or electricity traveling through a conductor, and the phenomenon is a change in the structure of an atom. So we'll go to the drawing, and I'll attempt to illustrate my point. So what's happening when this field interacts is that atoms that are normally, probably not the best way to do it, red, but anyway, so they have a proton with an electron traveling around, and there's a equilibrium in the sense that the strength of the electron and the strength of the proton have this could be considered in its native state a kind of ground. It's an average state of an atom, and when exposed to a magnetic field, or when current is passed through a conductor, the atom changes its orientation, and so the electrons end up biased to an end of the atom, and so in a sense it might still be a circle, but the idea is that now it has a decided bias. The electrons have been compressed in the sense that now they're closer together because they're pushed in a direction. So if they were static objects, as I believe they are in an atom, it just means exactly what I just said. They basically set up an arrangement where the perfect hexagon, let's say, let's make it a gon of distance between the electrons, is distorted, and it becomes flatter on one side, and shaped a bit different. And the point is that one side is electron heavy, and that if you viewed it from this side, the proton is the dominant player. So we could draw a proton strength like that line, and the electron is the weak player in terms of the pressure or the exposure. And then on this other side, the proton would be the weak player, and the electron is the strong player. And that's your difference from this ground, which would be where the two are equal in terms of how you view them from space. So in the neutral condition, viewed from some location, it looks like the atom's neutral. When they're biased, then viewed from a location, the bias is exposed. From this direction, it looks electron heavy. From this direction, it looks proton heavy. So basically, the one field is causing this effect, and this effect has two effects. First, it's creating a polar atom, and that means it's basically just creating a magnet. It's creating something that's got an end to it, a dipole, that's got a north and a south, or a plus and a minus. And in terms of its electrical potential, the higher pressure here is essentially voltage. So the electrons here have more voltage because they're under higher pressure. They're closer together. So as I've illustrated before, if you have two electrons close together and two electrons far apart, the force bits that are bouncing back and forth between them to push them apart, and that's literally what happens. Little bits are bouncing back and forth. When they're closer together, the impacts are increased dramatically as you move them closer together, which creates a lot of repulsive force. So there's more and more repulsion as you get closer and closer together. And that fits perfectly with this analogy of higher pressure, and that these atoms transfer that pressure. So as atoms hit each other, if one has high pressure electrons, it transfers that pressure to the other atom, and they both become an average of that pressure. So if this one was 10 pressures and this one was 5 pressures, they'd hit and become some 7.5 pressures units. So I just wanted to illustrate what I mean by there's no electric field. There's just one field that creates both phenomenon. By polarizing the atom, you pressurize the electrons. By pressurizing the electrons, you polarize the atom. Both circumstances, the two effects can't be, well, I can't say they can't be separated, but in a sense, they're usually going to cause each other. So pushing electrons together with voltage is going to polarize the atoms. Polarizing the atoms by exposing them to a magnetic field is going to pressurize the electrons. So the two effects were tied together. There isn't two separate fields that cause the effect. The one field causes both effects. And I think the one field is best described as a magnetic field, not an electric field. Electric is stuff, is the pressure moving from atom to atom. That's electricity. That's where electricity begins and ends, essentially. And the rest of it's magnetism. And magnetism can cause the pressurization of something. It can cause something to start doing that, to start moving electricity. But it has to go through magnetism first to get to pressurizing the atoms. The atoms are pressurized by magnetism. They're not pressurized by an electric field. They're pressurized by the magnetic field. All right, I think that's a good enough clarification to move on. And such. This goes down, and there's Professor Lewin, and so leave us continue. Hopefully.
Easiest symmetry that we have in 802. Now I will present you with a second form of symmetry, which is a flat horizontal plane. And I want you to work out most of it, but I'll help you a little bit to set it up. Suppose we have a plane which is very, very large. Think of it for now as infinitely large. It doesn't exist, of course, infinitely large. And I put on this plane charge. And I put a certain amount of charge density, which I call sigma.
Which is annoying that they call things all these weird things. So density just means an amount over a volume. So these thought experiments essentially of infinite planes, which can't really exist, but the idea is a practical matter. They exist a lot in the sense that atoms are tiny little things, and they're basically acting as little point sources. They're little suns, you could think of them as. And the forces they irradiate are from their little sun position. And you can sort of understand that when you have a big surface and you meet it with another big surface, those little tiny things, are shooting rays out in all directions, but the rays going this way still can't miss the other surface because the thing that's shooting it out is so small that sideways is only a tiny, tiny bit. The stuff that will actually go completely parallel to the surface, almost nothing does, because the atoms are all kind of recessed a little, so they can't even shoot stuff perfectly parallel. And because the plane's so much bigger than the atom's position, a very little gets out, escapes out the ends, you could say. So almost any two surfaces for a big pile of the atoms, it's almost like the other surface looks like an infinite plane. And that means no R squared rule. it means that every bit of force, or most of the force, is going to hit the other side, no matter which direction it goes in. It's going to hit. So it's an interesting thought experiment, because in a sense you could actually imagine creating a panel of LED lights that no matter how far away you got from it, you got exactly the same amount of light. So no matter how far away you went, you go 10 miles away and you're getting the same light you got when you were 2 feet away. So it's an interesting thought experiment.
Sigma is an amount of charge Q per area A. So it is a certain number of coulombs per square meter. And it's uniformly distributed, so the whole plane everywhere has the same number of coulombs per square meter, or microcoulombs, or nanocoulombs, whatever you prefer. And this is a plane which is huge, and you're being asked, what is the electric field anywhere in space? Just like we ask, what is the electric field anywhere inside the sphere and anywhere outside the sphere? Now I want to know what it is anywhere in the vicinity of this plane.
Right. So
now you pick a clever Gauss surface.
The answer is it's the same everywhere, because there's no, you're getting hit from all the other little bits. So any place you go, you're getting hit by exactly as much stuff, no matter where you go. So you can't get less. You always get the same. Your neighbor's stuff, the little atoms everywhere else are shooting lines at this way. So it's like me being exposed to gravity. If there's nothing blocking it, then it's the same from all directions.
It pops out very quickly. If you would choose a sphere as a Gauss surface, you're dead in the waters. You get nowhere because there's no spherical symmetry. I will define for you that Gauss surface, but I want you to work out at home how you get the electric field. Suppose I want to know what the electric field is at a distance d above the plane. What I do now is I choose this as my Gauss surface. Watch me closely. This is the intersection with the plane.
Alright, so the trick here is to use a surface that has reciprocal so they can cancel out. So the circle, we already found out, is very good at doing that, because you only have to do one line and all the other lines are the same. And so putting one above it, the plane, and below the plane, identical, you also get to do the cancel out thing. So you really end up with just a rod or a line. When you cancel everything else out, you just have a line. And the line is going to be, everything's the same. Doesn't matter how long the line gets, it's always the same answer.
This is my Gauss surface. It is a closed surface. 3 conditions have to be met for you to be able to calculate what the E vector is at that location D. The first one is that this is a flat plane here.
The E vector is kind of obvious. You already said this is a flat plane that's infinite. And if it's a flat plane and it's infinite, you can just surmise it has to, the E vector has to be perpendicular to the plane. It can't be anything else. There's no irregularity to force it to be any other angle but perpendicular. The natural, as they say, natural to the plane has to be natural.
And this is the same flat plane, must be parallel to this plane. That's a must. If you don't do that, you can't use Gauss' law. The second one is that these vertical walls that you have here are indeed perpendicular to that plane. In other words, these are parallel, and these are exactly vertical. If you don't make them vertical, if you do this, you're dead in the waters. You can't use Gauss' law very effectively. And then the third argument, which is very important, that this flat surface is a distance d above the plane, and that this flat surface is exactly the same distance below the plane. And you can already smell why that is important. Because if you ever want to use a symmetry argument, if this plane is uniformly charged, the electric field vector here, in terms of magnitude, obviously must be the same as there in terms of magnitude, maybe not in terms of direction, as long as this d is the same as that d. So that's why it's important that the two d's are the same. And the only charge that you have inside when you apply Gauss's law, is the charge which is, of course, here. That's the only charge inside that closed box. If you work this out...
Yeah, so it's not a closed box, it's a surface, and so it's just the piece of the surface cut out, but whatever. See, I just don't see the necessity of all this jargon. I think you could just establish rules that if you have a parallel plane, you already kind of know you're stuck with a straight line going up.
At home, you will find an amazing result. You will find that the electric flux through these vertical walls, zero. Nothing comes out through the vertical walls. Think about it, why that is. Your symmetry arguments. But something comes out here.
So he's just meaning that everything that goes into one of the lines, the sides of the wall, there's a reciprocal one coming this way. So every single one is met by somebody else pushing the other way. So the walls can't be moved.
Or comes in here if it is a negative charge, and something goes out here. And so you only have two contributions from those two end plates. You'll work on that, and you will find, perhaps to your amazing result, that the electric field equals sigma divided by 2 epsilon 0, and that it is independent of how far you are from that plane. Whether you're very far away or whether you're close, it's the same.
So the 2 epsilon 0 is still a very small number because the epsilon 0 is the permutivity of space, which is apparently really close to 0.
This is that plane, and if the plane is positively charged, then E would be like this here, and E would be like this here, and it would be independent of distance. And if it is negatively charged, E would be like so, and it would be like so, pointing towards the plane, and in all cases would the magnitude be sigma divided by 2 epsilon 0. Does it mean if I go very far away from that plane that it is still independent of the distance? Yeah, if that plane is infinitely large. But if the plane is only as large as the lecture hall here, then clearly it would hold very accurately as long as I stay relatively close to the plane. In other words, if my distance to the plane is small compared to the linear size of the plane. But if I go miles away, well, of course, then that plane...
So again, all of this is just getting to the point that the inverse square law isn't a law, okay? It's a tendency. And the law breaks down when you get really close. Two objects get very close, inverse square starts to lose meaning.
Is charged looks like a point charge. If I'm 5 miles away from 26,100, if the plane is only as large as this lecture hall, then it looks like a point charge, and obviously the electric field will then fall off as 1 over r squared. So when I say the E field doesn't change with distance, it means, of course, that you have to be relatively close to the surface, relative to the linear size of that surface.
Another point to make, I guess, is the actual thing producing the force has to be a minor part of the surface. So this doesn't hold, like you can be really close to the Earth and you're not going to undo the inverse square law because the Earth is radiating as one point particle. And so you're still missing a lot of force because you're still a small thing by comparison to the thing radiating. So it really has to do with compound surfaces, I suppose. More than one source, or a source that has a complex structure in the sense that it has 2 elements. It has an interior charge and an exterior induced one.
So you are going to prove this, and I'm going to use this now to calculate for you a much more complicated configuration of 2 charged planes. But I use that result. That's very important. And suppose I have here a plate, very large. Nothing is infinitely large, of course. And it has a surface charge density plus sigma. And I have here a plate which has surface charge density minus sigma. And the
I'm just thinking that there is something to mention, that a lot of these things they say, where they talk about symmetry and superposition, and superposition is just adding them up, and adding them up works. But the truth is that breaks down too in a lot of circumstances. And for example, if if you have two different charges, three different charges in a circumstance, there will be some effect if one of them is essentially turning into a dipole because of proximity. That, well, if they're connected. So they have to be a real dipole in that they have to be magnets. So if they're magnets, it wouldn't hold true because the magnets will affect each other. They'll start bending pieces of each other. And so the field configuration will be warped by the fact that the individual magnets, you have to calculate their effect on each other first, as in terms of changing their field, before you can calculate the fields.
Separation between these two plates happens to be D. And the question now is, what is the electric field anywhere in space? Here, here, and here. And we'll think of them as being infinitely large, each plate. And I now use the superposition principle. I say to myself, aha, this plate alone, forget this one, this plate alone would give me an E vector, stick to my colors, give me an E vector like so, and that is sigma divided by 2 epsilon 0. This one is also pointing away from this, sigma divided by 2 epsilon 0, and here it's also sigma divided by 2 epsilon 0, because it's independent of the distance to this plate. What is the negative charge doing? Well, the negative charge has E vectors pointing towards it, so here I have an E vector which is sigma divided by 2 epsilon 0. Here I have one that is sigma divided by 2 epsilon 0, and I have one that is pointing towards the plate, which is sigma divided by 2 epsilon 0. I use the superposition principle. I can add electric vectors, and when I do that, I find that these two cancel each other out. So the electric field here is 0. The electric field here is sigma divided by epsilon 0. The two support each other. They are both in the same direction. And the electric field here is again 0. And that is an amazing result.
Technically it's not, but fine. It's another cancellation argument from the pink one to the outside relative to the blue one to the outside. Those cancel out. But the field itself, if you put a depends on what you test with. Okay. But at the and of course it has to be infinite again, because at the edges it isn't going to be at all 0.
Of course, it's only accurate if these plates are extraordinarily large.
Okay.
And so if I have to draw the field lines in a situation like this, then the field lines would be like so if the upper plate is positive, and the field in here would be the same everywhere, the outside 0 and outside 0 here. Now, clearly, this cannot be true if you get into this area here where you are near the end of these plates. That is not possible. Why not? Well, you can't use your symmetry argument, so Gauss' law is not going to help you.
Again, it gets a little bit complicated because you have to think in terms of, okay, it's an infinite plane, and nothing's going to be an infinite plane. And in this case, it gets a little bit more complicated in terms of, like I said, especially the ends. But the fact is, there isn't that there's no field, it's that there's two. Again, it's that idea of a neutralized field. There's a field, it's just mixed. And therefore, you do this.
If you get anywhere near this area, and it is very difficult to calculate the electric field configuration when you are near the edges, which we call the fringe field. Maxwell, of course, was a clever man, and he knew how to do that. Today we can also do that very easily with computers, but I'll show you from Maxwell's original publications that in a situation like that, he was already perfectly capable of calculating these electric field lines. And you have these two horizontal plates, which one is plus and which one is minus, doesn't matter. He doesn't put arrows in there. And what you see...
Yeah, it's very good that he doesn't. I mean, obviously he's drawn a whole bunch of field lines. You can see them coming out of the... I mean, the ones in the middle are obviously going up and down, but clearly the end ones do go across the charge, so you can't say there's no charge if there's a charge, but anyway, I'm not going to argue with it.
is an extremely strong field inside the two plates. Remember that the density of field lines tells you something about a very strong field.
Right, so the tightness of the lines say it's very strong, the big fat lines say it's weak. So there's still a field on the outside, it's just weak.
But when you get near the edge, the field is not really zero. The field strength drops very rapidly because look, the density is very low, but it is not zero, and the electric field is not zero here either, and is not zero there. In our assumption, in our simplification, we have, however, assumed that the plate is so large that we don't have to worry about any end effects, and in that case, the electric field is only existent in between the plates, but not anywhere else. I now want to...
Well, again, I'll just point out, it's there, it's just that it's been canceled by being half going this way and half going that way.
Demonstrate to you some of the things that we have learned today. And the first thing that I want to demonstrate is that the electric field outside a large plane is more or less constant. Doesn't matter how far away you are. Now, the way I'm going to do that is, of course, I don't have an infinite large plane. The plane that you're going to see only a few square meters in size. And so it's only something like 1 by 1 meter. Then it would only be true that the electric field is very close to constant if I stay very close to that plane. The moment that I go out as far as a meter, of course, it's no longer true. So it's very qualitative what I'm going to show you. But you're going to see very shortly there a very large plane. I'm going to get it in a few minutes. And let's assume that we look at that plane edge on.
All right, the word qualitative and quantitative, they use these words, and I don't know exactly why they do. Because to me, qualitative should mean that it's precise evidence, and quantitative means, you know, it's a bulk. But that's just me.
So here is that plane. Look at it from edge on, it will be put here. It will block your view, that's why we don't have it up now. And what I will do now is I will connect that with the Van de Graaff, which is behind it. If you wait a few minutes, then class will pay attention to me and not to you. Here's the Van de Graaff. We're going to attach it to the Van de Graaff. And then we use this interesting fishing rod, which is a small Mylar balloon, which we will charge with the same charge as the Van de Graaff, the same charge as the plate. And we will hold that in front of the plane. And then, of course, there will be force. So here is my glass rod. This is the vertical. And because there will be a repelling force on this air-filled balloon, there will be an angle. There's an electric force on it because the two have the same charge. And this is the angle theta that I will show you, projected on that wall. And when I move...
So it's just a demonstration of the fact that there's no inverse square law, that the angle will stay substantially the same. That is, the intensity of the force will remain constant for quite a distance. So that's all this is to illustrate, is that if you have a large enough surface, the inverse square law breaks down at distances that are some smaller percentage of that surface area.
Move this away from this plane, you will see that the angle theta becomes smaller. Yes, of course, because look how small that plane is. No matter what I do, if I go from 20 to 40 centimeters, you can't really say that the plane is infinitely large compared to 40 centimeters. But you will see that the angle of theta will change very slowly. And then we will remove that plane, and then we will do exactly the same experiment, but we will use only the Van de Graaff, which produces now an electric field. And that electric field now falls off as 1 over r squared. It's not constant as a function of distance, but it falls off as 1 over r squared. This is a hollow...
So the interesting thing to do would be to take that and then do the dipole experiment. That is, charge another Van de Graaff or just another metal ball. Let's see, it's hard to make it the same density of charge. So you need another Van de Graaff producing the opposite charge in proximity to the first one. And then you could maybe approximate the r cubed. That is, the field diminishes even faster, gets weaker even faster. So that would, I think it would have helped to do that.
Sphere. So you can think of it as all the charge right at the center, as we demonstrated. It's on the blackboard still here. You know, you get that amazing result. And so now, if I place this fishing rod, this balloon, near the spherical Van de Graaff, you will see that this angle theta drops very fast when I start moving my hand away. Extraordinarily fast. If I double the distance to the center, the force on that little object will become 4 times smaller. It's inverse r squared. So let's first do the
And I guess in the case of cubed, it would be 9 times, so, which is a lot.
Plane, and then we'll try to do the single Van de Graaff. And we'll try to optimize the light conditions. We have a projection here. There's a carbon arc, which will hopefully produce some light in that direction, if the carbon arc works. Michael, oh, I forgot to turn on the power. Thank you. So this carbon arc is coming on now, and you'll see there the shadows on that wall. See my hand? Here is that plane, and it is far from infinitely large, that plane. If I were this far away from it, 4 centimeters, very close approximation, it would be infinitely large. But if I'm here and there, and that's where I will be, of course, it is not infinitely large.
A little excessive. You know, yeah, we get it.
Anymore. So let's start the Van de Graaff. You can't see, but I turn it on. It's rotating now. I have to put charge on here, so I'll touch it with the Van de Graaff. And so this is now charged. It has the same charge as the plane. The plane is being charged, and here you see the angle. Try to remember that angle. It's hard to estimate, maybe 15 degrees. You see the vertical. And if now it's about 30 centimeters away from the plane. And if now I go back to 50 centimeters, which is where I'm now, you see the angle hasn't changed very much.
So the other thing you should have pointed out was that by putting this big sheet in front, he's radically reduced the voltage of the Van de Graaff on the flat plane. So the angle is only 15 degrees at its strongest, where when he uses the Van de Graaff alone, it's probably going to be a much larger angle. So you should have just pointed that out, because the voltage is going to be much higher.
If I go further out to 60 centimeters, yeah, the angle goes down a little. Of course it does, but not very much. And if I go far away, all the way to Mass Avenue, of course, the force on this little object would be inversely r squared, because then the whole plane would behave like a point source. So I've shown you that very close to this plane, the electric field stays approximately constant. So if now we remove this...
And that there's a clear relationship between this voltage thing, how much pressure you're creating, and how much you're creating magnets. So you make them more magnetic by creating more pressure. More pressure means electrons further away from the proton, more compressed, more on one side and less on the other side of the proton, and therefore the atom is more and more polarized the higher the voltage.
Marcos, if you can, we'll have to take this also off. Thank you very much. So now we have the Van de Graaff alone. So now we know that the electric field falls off as 1 over r squared. That's a very good approximation now. We can think of the charge as being right at the center. I will give it a little bit of charge. Oh, it is already charged. Okay, so look at the projection. The balloon is now, maybe 30 centimeters away from the center, maybe 40. Oh, the angle is almost 45 degrees. And now I double the distance. I go to about 90 centimeters, and look at that angle theta. The angle theta is now down to, maybe 10 degrees. I will go back where I was. This angle is about 40 degrees, and now very small. And when I go here, which is about 1.5 meters, you can hardly see that there's any angle. It's only a few degrees. And so I've shown you only qualitatively that the electric field falls off very...
So I would argue that it's not very qualitative. It's a little bit not perfect. And, it almost looked like it wasn't really the inverse square law. It looked like it was a little less than, the diminishment wasn't quite as dramatic as what you would expect of the inverse square law. But, who's quibbling?
Very rapidly in the vicinity of a hollow, uniformly charged sphere, and that it doesn't fall off very fast if you are in the near vicinity of a...
They really didn't need to throw that in. They take these little shots of the audience, it's a little cute chick now and then, or goofy guy. It's always cute chick or goofy guy.
Plane. The second thing I want to show you has to do with the fact that the electric field inside a uniformly charged sphere 0. Here I have a sphere which is not entirely closed. I can't make it closed because I want to demonstrate to you that there is no electric field inside when I charge it uniformly. And since I have to get inside, I need an opening.
Right. All right. So this is another one where I'd say he's saying it wrong. To say there's no field, what he means is the two fields cancel. Wherever you go, you're getting pushed, but you're getting pushed exactly as much from one side as the other side over time. So you might be jittering in there. So technically, when he goes to create a dipole, he might be collecting some of the difference just because he has two objects in a different location when he separates them. And so I'm not quite sure everything he says here is exactly accurate.
There's nothing I can do about it. Since there is an opening, the electric field is not exactly 0 inside. It's open.
Well, the other problem with the opening is the opening has all kinds of weird crap around it. So whenever he puts something in, the thing he's putting in is going to be affected by the field around the opening. So it is going to distort it to some extent. It can add or subtract charge just by passing it through the opening. Through induction.
Only true if this is a complete closed surface and if the charge is uniformly distributed. But it's a good approximation. The opening is quite small. And what I'm going to do is I'm going to charge this sphere. I'm putting charge outside. I use a device that we have not used before, but that's not so important. But here is now that hollow sphere. I'm going to put charge on there. Let's suppose it is positive charge. So this will be positively charged. Since it is a conductor, as we will learn, I think the next lecture, or at least this week, that the charge will automatically distribute uniformly. It only does that on a conductor. And now, to demonstrate to you that there is an electric field here, I will use induction. I have two ping pong balls painted with conducting paint. They touch each other. Under influence of this electric field, this one will become negative and this one will become positive. We've discussed that last time. You create a dipole. It's not important that it is a dipole. I separate the two. I have negative charge here and positive charge there. I will touch any one of these two balls, it doesn't matter which one, with the electroscope, and you will see that there is charge there. So I have demonstrated then that there is an electric field outside that sphere. Now I will do exactly the same demonstration, but now I put these two conducting balls inside. So here they are. I touch them. You just have to trust me that I really will touch them. And then I will take them out. And if I didn't make a mistake, if I didn't touch the rim by accident, then I will show you that there is no electric field inside. It means there is no induction. So these balls did not pick up charge. I'll show you with the electroscope.
Again, kind of the wrong way to say it. They pick up both charges. They're constantly having their charge changed. And I suppose if you shaped an item the right way, you might be able to pick up some energy that way. I don't know. I mean, it's just a fact that the charge is there. It's just they're fighting against each other. Just like if you were in the neutral spot between the Earth and the Moon, the two gravities are still there and they're fighting with each other. I could do something like the Earth could rotate to where a big mountain is, and it'd be a little more of a pull that way, and then you could rotate the Moon until there's a mountain and it'd pull a little that way, that kind of thing.
That indeed there is no charge on it. So that is the way I want to do this. So there's the electroscope. Here's the sphere. And the way I'm going to charge it has a nice name. It's called electrophorus. Hard to pronounce. I first rub a glass plate with cat fur. Then I take a metal plate.
I think they could have done this with something like some fake fur. I'm sure it'll work. It's kind of disgusting.
I put it on top, and I touch it with my finger. And now I transfer the charge. And you think about it, why that is. I put it on here again, touch it again with my finger. I'm again charging it. Put it on top.
Yeah, I'm not exactly sure why you have to touch it with your finger. I mean, it seems like the charge should go right into the metal plate. But I guess the point is it's an insulator, the glass. So to pull the charge off the insulator, you need a route to ground. So that's the key. If you want to get a charge off of a surface, the key is to use something like a piece of metal and touch it. And that way the metal will pull from the entire surface charge. And so you'll collect more charge that way. So that's why he's touching it. He's touching it to create a path for the pressure so it pulls off the entire glass surface, because it can't really pick up the charge because it's an insulator. Without, it needs the current to move, and the insulator won't make a current, so it has to pull the charge all up at once. You can't move it across and come up one place and move it across and come. The insulator won't do that. The glass especially. Glass gets charged in like little dots, and the charges can be different, the little dots and all that crap.
Touch it again with my finger. I want a little bit more charge. So I'm rubbing.
And so he's picking it up with an insulated handle. So once he pulls it off the glass, the metal will automatically average the charge. So even if the glass has a bunch of uneven charges, like a few little hot spots on it, so it has mostly little black things, and it has a red thing here, red, 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 red. Once he pulls it off, the whole thing will just go to one kind of color of black. I mean, a certain level of it, a certain amount of pressure. So the glass might have primarily 150 volts on it, let's say, but it has a few of these negative voltages stuck in there. And so when he pulls it off, he has picked up both of those, and the conductor will basically do the addition and subtraction and come up with a total of 125 volts or something as the net product. And he's picking up with an insulated handle, so now he has 125 volts, and now he can touch something else, and now it'll average again. So if the thing he touches is lower voltage, like 80 volts, then the 120 volts, 25 volts will go into the 80 volts, and it'll come out with an average based on the density of the two objects. So the average might, if it's a real heavy thing that you're touching, then it's going to take you a while to increase the voltage because of the charge. It has a capacity to hold.
This again. Put this on top. Touch it with my finger. Every time I do that, I feel a little shock. Put it on there. Touch it with my finger. Okay, let's hope that's enough. So now comes demonstration number 1. These two spheres is conducting, completely discharged. I bring them close to this sphere. There they are. I separate them. And now they must have picked up charge. Shall I use this one or this one to touch the electroscope? The same to me. My right hand or my left hand? Who wants right?
Who cares?
Who wants left?
Who cares?
The right won't have it.
The one in the middle.
So I've shown you that there is an electric field there. Through induction, I've created charge on here. Now I'll do the same inside. It's always tricky, because if I hit the rim, then it's not zero. This one has to go in first because the opening is too small. Then the second one has to come in. Now I have to touch them.
He hits the
really
sides
I
anywhere.
wouldn't cheat on you. Not this
It'll
time.
pick up the charge.
They're now in contact with each other. And now I take one out. And I take the other out. Which one shall I touch it? There shouldn't be any charge on either one of them. We had left before or we had right before? Well, let's do this one. This one? Who is for left? Who is for right? The left have it. Nothing. Maybe a teeny little bit. Well, the electric field inside is not necessarily exactly zero, but it's extremely close.
So I don't think he should have said that, but the point is that when he pulls them out through the opening is probably where a little bit of charge is induced.
The last thing I want to show you has to do with the fringe field that we have seen here. I have here two parallel plates which I'm going to charge with an instrument that we have not seen.
I like parallel plate experiments. These are always interesting. Yeah, you pull them apart, the voltage increases, all kinds of different things. It's good physics.
Before, which is called the Wimhurst. If I rotate this crank, I can produce positive and negative charge. And this plate becomes positively charged and the other plate automatically becomes negatively charged.
I wish he would tell us what these things are when he's, I mean, I guess the Windhurst is a bunch of magnets and you push them through a coil or something, I imagine.
And I'm going to show this to you. Right there, that's the idea. Yeah, we'll make it. So there you see these two plates, and you see a ping pong ball. And this ping pong ball is a conductor. We put conducting paint on it. And remember when I did the demonstration with the balloon, which bounced between my head and the Van de Graaff, and every time that it bounced on the Van de Graaff, it took all the charge of the Van de Graaff. When it bounced from my head, it took my charge. And so it went back and forth. And that is what I want to show you now, that this ping pong ball will start to probe that field first outside the capacitor, or I shouldn't use the word capacitor, but these plates, and then I will bring the ping pong ball inside, and then you will see that the field is much stronger there.
So I think if you use something not rigid, that it might stick. But that's just my guess. It'll stick, and it could just stay there. Like the confetti, some of the confetti stayed on top of the Van de Graaff. So it needs a little impetus to get off of the... It has to rise above it a little. I mean, that might be an interesting experiment is to put an insulator between the confetti and the Van de Graaff and see if more confetti flies off that way. But the insulator, the surface is still charged, so it might not help.
Well, let's first get some charge on there. And listen to the sound. Every time that it hits, it bangs. So it's following almost those field lines.
So it's not really following any field lines. So that's just, it's being, first it's on a string, so it can't go where it wants to. Understand that. And it's going, and then the string is pulling it. So, I mean, that's part of what you have to understand. So if it was free space, the ping pong ball probably wouldn't, it would have too much velocity. It wouldn't go back to the other side. So the fact that it's following field lines is just coincidence.
And in doing that, it's actually transferring charge every time from one plate to the other. So it's nicely going around in an arc, the way you see it there. So it's clear that there is an electric field outside. I've proven that to you, otherwise it would never do what it's doing. So the electric field outside is not exactly zero, of course not.
Okay, so the electric field outside, what he means is when you don't have an infinite plane. So at the edges, there's a strong field, a stronger one. Towards the middle, there's less. But it's not less field, it's just that the two fields cancel.
This plate is not infinitely large. And now I will bring this ping pong ball inside. I have to open up the gap a little.
Good. This ought to be good.
And I will bring it inside. And you see the field is much stronger.
All right, so this essentially illustrates what I've been telling you about ping pong ball paddles and the force, the electron. This is the opposite effect, obviously, because the ping pong ball is changing its charge, and that's why it's bouncing. But I wonder if you could do it with same charges. There must be some reason it just doesn't work, but it should work. But the point is, it just is a good illustration of the fact that you can obviously see the further apart you put them, the slower it'll bounce, the closer they are, the faster it bounces. And each hit, in theory, in an atom would be exactly the same amount of energy. So there wouldn't be anything called less energy. It'd be the same impact. So it's just a number of impacts tell you how much energy there is. So the proximity equals energy. Pushing things together is energy, because it's going to take you energy to do it.
Now it's going back and forth between those very high density field lines, very strong electric field, going back and forth. Each time that it hits the plate, it changes polarity. And this is not too different from the experiment I did with the balloon when I bounced it back from the Van de Graaff to my head and back to the Van de Graaff. Okay, start working on that assignment. It's not an easy assignment this week. See you Wednesday.
Yeah, so I like that. Anyway, yeah, so I think that's we're through 3 of them, so far so good. And I don't think there's anything I have to add. Probably something worth adding, but I just don't remember it, or it doesn't occur to me at the moment. And so, yeah, I won't add it. So till the next time, and such.